Okay, so this is ELEC142 Semester 2 Problem Sheet 4 Solutions Part 3. In this problem set we're going to be looking at how to solve questions 7 and 8 of our problem sheet. So by now you've completed the rest of these questions on the problem sheet and you're in a position to be able to tackle these really quite tricky ones which you've got left. So question 7 isn't too bad. Question 8 is a bit nasty. So let's have a look and see what the solutions are. So let's look at question 7. You'll see the working on this gets a little bit long. So as you can see, I can zoom out. It can still get it in a page, but it's starting to get a little bit longer, this one. So let's just zoom back in because it's easier for you to see what I'm doing as I solve it. So let's make it the page width. So what I've done first up is I've redrawn my circuit. So I've got my inductor in series with my 2 ohm resistor, which I've called XR1. Just because I've got 2 resistors, I had to give it a number just so we knew what was going on. And in the second branch, I've got a 6 nanofarad capacitor in series with a 3 ohm resistor, which I've labelled XR2. So I've got 2 resistors of different values, and I have to take that into account when I'm working out the reactances. So step 1, as always, let's work out those reactances. So the inductor is equal to J omega L, which I've just jumped straight into the rectangular form here. So it's 0 because there's no real part, plus 2.5 times 10 to the minus 5 J ohms. The reactance of the capacitor XC is minus J 1 over omega C. Putting the values in, this time we get 0 real part, minus, because it's a capacitor, 3.3 times 10 to the 5 J ohms. Remember, nano is 10 to the minus 9, so that's what we've got here. Okay, and because we've got both nanos, we can see that they both end up the same order of no, they're not the same. Yeah, they're the same order of magnitude, but in reverse directions. So this was nanohenries, this is nanofarads. There's a lot of duality between between inductors and capacitors. They work in opposite ways. They are basically opposites of each other. And if you think about the frequency behavior of these components, you can see that as well. And that's why when we went on to filters, we could make filters, a low pass filter or a high pass filter, from a combination of a resistor and a capacitor, or a resistor and an inductor, just by switching the positions of those because of the duality of them, as it were. Anyway, back onto the problem sheet. We're going to find out the reactances of our resistors. So XR1, that 2 ohm resistor in full rectangular form, is 2 plus 0 J ohms, and XR2, which was our 3 ohm resistor, becomes 3 plus 0 J ohms. So far so good. That was step 1. The next step is simplification of the circuit. So you can add additional steps into here if you want, but because we've got series combinations, I've just done it straight up. So what we can see is that we can replace our resistor and our inductor with a single complex impedance, which I've called ZLR because it's a inductor and a resistor chain. And we can combine this branch, which is our series combination of a capacitor and a resistor, which I've called ZCR there. So what we've done is I've replaced these 2 components with a single impedance. We can see these are in parallel with a single component which replaces these 2. So let's work them out. Because they're in series, it's dead simple. ZLR, which is our inductor branch, is the impedance of the inductor plus the impedance of resistor 1, which gives us 2 plus 2.5 times 10 to the minus 5 J ohms. We do the same thing for our capacitor and our resistor branch. Add the reactance of the capacitor to the reactance of the resistor, which gives us 3 minus 3.3 times 10 to the 5 J ohms. So far so good. So now we've got to this stage, that's very similar to what we've had before. And if you look at this, we can see that they even look like 2 resistors in series. So we can apply this parallel rule, 2 resistors in parallel. We can apply the resistors in parallel rules to get our final value of Z total. And what we can just write that is Z total is equal to ZLR in parallel with ZCR, and we can apply the product and sum rule just as we would for resistors. So that's what I've done there. So now, if you've got that far, you've understood the reasoning behind what we're doing. The rest of it is just manipulation of the maths to make it work. So put your values into the equation. So we've got Z, there we go, ZLR on this side because that's the resistor and the inductor contribution, and ZCR on this side, which is the resistor and capacitor combination. Same as we've done before, we've converted the top parts into polar form because we want to multiply them, and the bottom part, the denominator, we've just added those two rectangular parts together. So next step, we've performed that multiplication, and then we've done the next step, we've just converted this into polar form because we want it in polar form because we do polar division. Interestingly, you can see that, oh, don't worry, no you can't, ignore me. Oh yeah, that's right. So this is where the angle is very, very similar to this angle because that really is dominating the response, because this is a very small angle in comparison, so it's almost like we can ignore it. The magnitude is a lot simpler to see, it's just 2 times that one. So remember, when you're working in polar form, you've got this magnitude component and the phase component, and they are 2 different things which are combined together a lot more subtly in the rectangular form. So where do we got to? We've got to this point, so we've got both of these in polar form. We do that polar division, so we take the magnitudes and divide the bottom magnitude by the top magnitude, and the angles we minus the bottom from the top one, and that gives us in polar form a magnitude of 2 at an angle of 2 times 10 to the minus 4 degrees. I should really have written degrees here. I didn't put a degree sign because that would look really confusing because this is a really small angle. So either write it out in full or write degrees afterwards, because if I put a degree sign up there, it might look like 2 times 10 to the minus 40, which isn't correct. So it's got to be clear what you're trying to get across. And then we've got just converted that into rectangular form. So the final answer is 2 plus 6.98 times 10 to the minus 6 J ohms. And that's the answer. So hopefully that wasn't as confusing as you thought it might be looking at it. If you can take this step where you can go from these bits in series and simplify them, it suddenly becomes a lot easier to deal with this, because this looks like a lot of things we've looked at before. So that was, yeah, quite a difficult one. Let's go on to question 8. Now this is, if you can do this, you're doing really well. This is a bit of a difficult one because the whole point of this course is that we've got to stretch the people at the top end as well. So this is our circuit. It looks a little bit horrible to begin with, but what we're going to do is we're going to go through the simplification steps and we're going to see how we can solve this. So let's look at question 8 and let's see, how long did this take? How much space did this take? This took a whole page. So this is the working. We're going to go through how I did this. Let's just zoom back in. So what I want you to see before I dive into the working is we've got just more, the more complicated the circuit is, the more steps you're potentially going to have to do before you can simplify it. But the main process is the same. So start with your circuit, work out the reactances of everything you've got. So that's what this part of the answer is doing. So that's a lot of the working done already, and it's just because we've got so many components it takes a bit longer to do that. Make sure your labels are clear and you know what's going on. That's half of it solved. The next step is to simplify the components that are in series. So what we can see here, hopefully this will work, is that these are in series, this capacitor and this inductor are in series, so we can replace it with a single impedance block. The other part is slightly more tricky, and by redrawing it, hopefully you can see it because it's not presented in the way you've seen before. This is why it's a little bit sneaky, is because this resistor, as we can see if you follow it around, is actually in series with this capacitor and this second resistor. So we can replace these components with this single impedance element here. That's kind of the tricky bit there. And then once we get to this stage, we can see again what's going on. So you can see split it up. Here we go. So these ones are in parallel and we can replace these components with this single one, Z1 here. And when you get to this stage, you can see really clearly that these are just in series, so you can then replace it with a single one. So there's more steps, but if you conceptually understand what's going on, you've won the battle. So let's just zoom in so we can see a bit clearer at the top. So what have we got? Well, first up, I said I was calculating all of these reactances. So I've chosen this time, instead of calling them XR1 and XR2, is that I've labelled them with a value that should make sense. So this is XR1 100, so this is the reactance of the 100 ohm resistor, and XR30 is the reactance of the 30 ohm resistor, which is here. So XR100 is going to be the same, so that's 100 plus 0 J ohms in rectangular form, and if we calculate XR30, this one's 30 plus 0 J in rectangular form. That should be so far so good. We can use the same value because these two 100 ohm components are the same. Then we've got two capacitors here. We've got what I've called XC6, which is the reactance of the capacitor, which is 6 microfarads. It really doesn't matter what you call it, as long as it's clear which one you're referring to. And what I should really have done is written on this diagram which labels I'd use for each of these, like I'd done in the previous question. So that was bad on me not to do that. But I'm following what I'm doing because I've used sensible labels, so it makes it a bit clearer for me. So just work out the value. Again, put your omega value and your C value in, and for XC6 we get a value of 0 minus 33.3 J ohms. XC2 this time is the 2 microfarad capacitor. That gives an answer of 0 minus 1000 J ohms. Micro is 10 to the minus 6. Make sure you've got that right. Then XL, we've only got one inductor in this circuit, so I haven't given it another label after here, it's just X of L. That's J omega L, which if you put the values in, you get 0 plus 7.5 times, work that out, okay. You get 0 plus 7.5 J ohms. This looks slightly confusing because omega is 500 times 15 times 10 to the minus 3 because it's 15 millihenries. I should have put a bracket there, it makes it a bit less confusing. But, you know, if you get out the right answer, it's not so bad. But please, please, please make sure you show you're working if it's not explicitly clear what's going on. So that was step 1 done. Those are all the reactances. Now we're ready to do the simplification steps. So first up, we can see that, let's draw this here, these two components are in series, and I've called it ZCL. So ZCL is equal to the reactance of capacitor, which is 6 microfarads, plus the reactance of that inductor. So I'm just adding these components together in rectangular form because that's easier. And we can see we get an output value of 0 minus 25.8 J ohms. So what effect that's having is the resistor and the inductor are opposites, so they're kind of fighting each other, and you end up with something in the middle, which is mostly dominated by that capacitor, as we can see, because this is a lot bigger, and we've ended up with a minus value. So that's what we can see there. In reality, this circuit is testing your comprehension. There are reasons why you would put a capacitor and an inductor in series, which we're going to come on to when we look at resonance, but for now, this is just a sort of academic example to get you to think about what's going on. So that's so good, that's ZCL. Next up, we've got this second part. So let's just scroll up a tiny bit so we can see what's going on. So this time, we want to find out what's the complex impedance of this resistor in series with this capacitor in series with this resistor. So I've called that ZRCR because it's a resistor, then a capacitor, then a resistor. You can call it what you want. I just found that easier to understand. So we can see here ZRCR is going to be equal to the reactance of the 100 ohm resistor plus the reactance of the 2 microfarad capacitor plus the reactance of the 30 ohm resistor. So I've just put the rectangular form of these numbers here. Because they're on rectangular form, you can just add them together. So it's 100 plus 30 plus 0, that's the real part, so that's 130, and the imaginary part is 0 plus negative 1000 minus 0. So we get 130 minus 1000 J ohms. That's the value of that part. That's the first simplification step. Next up, we can see that these two complex impedances are in parallel, and we can work that out and find Z1. So it's the same as we did before in question 7. So Z1 is equal to ZCL in parallel with ZRCR, which is the product over the sum. So I've just put those values in. Shouldn't be too difficult to work out. If you've got this far, you're probably finding this really easy now. So I've just put the rectangular numbers in, converted the top part to polar form, added the rectangular denominator together, then I've done the phasor multiplication on this step, and I've converted the denominator to polar form. Next up we do this polar division, and we end up with 25.16 at an angle of minus 89.82 degrees, which we can convert to rectangular form as 0.079 minus 25.2 J ohms. So we can see that this part, this impedance, is really dominated by the capacitor term, because the real term's very small and it's a minus J going on here. Okay, so we're very, very, very nearly there. The final step is we can see that this XR100 is in series with Z1. So we just combine those to get our final Z total, or ZT. So just very quickly, that's what we do. We're working in rectangular form because we're doing addition, so it's 0.079 minus 25.2J plus 100 plus 0J. Just do that that rectangular addition, and we get a final answer of 100.079 minus 25.2 J ohms. So there we go, that's the final answer. Well done if you got that one. The kind of, like I say, if you understand conceptually what's going on, the maths is just secondary to it. The tricky part in this was very simple. You'd seen this sort of combination together. It was recognising that once you'd simplified all of this, it was just in series with this resistor, was kind of the tricky part of that question. So I hope you got that, and well done if you did.